Welcome to this explainer. If you're an aspiring network engineer or, just grinding through your CCNA prep right now, you're going to want to grab your notepad. This is an absolutely crucial topic. Today, we're diving deep into decoding network models, specifically focusing on the core architectural blueprints that make the internet actually work, OSI versus TCP IP.
So, let's start by asking a massive question. How do billions of completely diverse devices manage to communicate flawlessly? I mean, think about it. You've got smartphones, laptops, huge servers, maybe even your smart fridge, all built by different manufacturers running on entirely different hardware. Yet somehow they all manage to speak the exact same language globally, without causing constant network crashing errors. It honestly seems like magic, right? But it's actually just highly structured engineering.
To make sense of all this chaos, we use what's called a reference model. You can think of a reference model as a universal translation guide, or basically the rules of the road for network data. It's a conceptual blueprint that takes this insanely complex process of network communication and chops it up into logical, manageable layers. It's kind of like the Postal Service. You know how a letter goes into an envelope, gets handed to a mail carrier, sorted at a big facility, and then finally delivered? Well, every single step in that process has a very specific, isolated role.
Here is our agenda for today's explainer. 1. The rules of networking. 2. The OSI reference model. 3. The TCP/IP protocol model. 4. OSI vs TCP/IP differences. And 5. Why these models matter.
Section 1. The rules of networking. Let's dive right in and understand why these layered models are so vital, because without them, the internet as we know it simply wouldn't exist.
By segmenting messages and using specific protocol data units, layered models ensure seamless data encapsulation. Think of it exactly like those Russian nesting dolls. As your data travels down the stack, it gets wrapped up in a brand new layer, basically adding specific headers and trailers at every single step. This happens all the way from the software application on your screen right down to the actual physical copper or fiber optic cable. This layered structure is brilliant because it allows engineers to isolate functions. So if a piece of software gets updated, it doesn't just randomly break your physical hardware.
Moving on to Section 2, the OSI reference model. This is the most famous conceptual guide in all of IT. Honestly, it's the absolute gold standard for understanding network theory.
Now, if you are preparing for your CCNA or any technical interview, you need to literally burn this number into your memory. 7. There are exactly 7 distinct layers in the OSI model. And knowing these isn't just about passing a test, it's about forming a solid mental map of how data actually behaves across a network.
These 7 logical layers structure the complete journey of your data. They start at the very bottom with the physical cabling, that's layer 1, and move all the way up to your web browser or email client at layer 7, the application layer. Every single time you click a link, your request shoots down these 7 layers on your device, travels across the physical network, and then climbs all the way back up those same 7 layers on the destination server.
Let's break down some of the heavy lifters here, and we can group them into 3 main functions. First, the bottom layers move the data. The physical layer handles raw bits over copper or fiber, while the data link layer takes those bits, forms them into frames, and uses physical MAC addresses. Then the middle layers route it. Layer 3, the network layer, relies on routers to find logical paths using 32-bit IP addresses. And Layer 4, the transport layer, makes sure your data actually gets there reliably using TCP or maybe super fast using UDP. Finally, the top layers format it. Session, presentation, and application handle the actual software formatting and client-server interactions.
Section 3, the TCP/IP protocol model. So while OSI is this beautiful theoretical map we all learned, TCP/IP is the actual implemented terrain. It's the real-world standard powering the internet today.
Here's a quick insider tip for you, especially if you've got an exam coming up. While the original legacy TCP/IP model historically had 4 layers, the modern updated TCP/IP model that you actually need to know today consists of exactly 5 layers.
This modern 5-layer TCP/IP suite handles absolutely everything you need for communication. It scales perfectly from those client-server HTTP requests at the application layer, down through TCP segmentation at the transport layer, IP routing at the network layer, framing at the data link layer, and finally, network access at the physical layer.
Section 4. OSI versus TCP/IP differences. This is the crucial part. Understanding how these two models face off against each other. Why learn both, and where do they overlap?
The biggest takeaway here boils down to theory versus practice. See, the OSI model was built by committees striving for this theoretical perfection, which gave us that highly granular 7-layer structure. But on the flip side, TCP/IP was built by engineers who just needed to get the Department of Defense network up and running. Practicality won. Because of that, TCP/IP compresses a lot of those higher-level functions into a much more streamlined model.
When we look at them side by side, the core difference is super clear. TCP/IP takes the OSI's application, presentation, and session layers, layers 5, 6, and 7, and basically just absorbs them all into one single application layer. Everything below that lines up nicely. Transport maps to transport, network maps to network, and so on. Now, why compress them? Well, in the real world of software development, the application itself usually just handles its own session management and data formatting internally anyway. That rigid separation the OSI model has just wasn't necessary in practice.
To see how this works practically, let's think about a real-world technology like Ethernet. Ethernet operates squarely across the bottom two OSI layers. It defines both Layer 2 protocols and Layer 1 technologies. Basically, it acts as the bridge linking physical cables and electrical signals with data link framing, which allows your data to be placed properly onto the physical media. Zooming in even further, you'll notice the data link layer itself splits into two distinct parts: the logical link control, or LLC, and the media access control, or MAC. The LLC sublayer communicates upward, interacting with network layer protocols like IPv4 or IPv6. Meanwhile, the MAC sublayer is busy handling the physical hardware downward, managing data encapsulation and the actual media access control on your network interface card. It's a perfect example of how theory directly dictates how hardware is engineered.
Section 5. Why these models matter. Let's bring all this back to reality and answer the ultimate question. Why are you learning this? And why is mastering both models essential for your career?
The reality is you're going to use both of them constantly. You use the 7-layer OSI model to isolate problems in your day-to-day troubleshooting. It's a massive IT cliché, but it's 100% true. When the network goes down, you do not start by analyzing application code. You start at Layer 1, as in, is the physical cable actually plugged in? You troubleshoot using OSI to map out the problem logically. On the other hand, TCP/IP is the literal software suite running on the routers and switches across the globe. So the rule of thumb to remember is this: you configure TCP/IP, but you troubleshoot using OSI.
So, now that you deeply understand the structural blueprints of networking and the key differences between how OSI categorizes theory and TCP/IP executes it, a new challenge comes up. Having the map is great, but how do you actually drive the packets? Your next step is to explore the actual routing protocols, like static and dynamic routes running at Layer 3, that physically move data across these logical layers.